Now, the Bhopal disaster has been referred to as the Hiroshima of the chemical industry. It is a catastrophe unparalleled in industrial history. Imagine a scene of chaos and confusion as people are running from their homes, coughing and gasping for breath, their eyes burning. Some falling as they ran, vomiting and dying on the street. Imagine bodies piled on top of one another in trucks, taken to be cremated or buried in rows of mass graves. This is what the people of Bhopal were subject to on December 3rd, 1984, when 40 tons of toxic chemical gases were released from a pesticide factory in Bhopal, India. Residents of Bhopal woke up to fits of coughing as their lungs filled with fluid. Initial effects of the gas, which spread to up to 40 square kilometers, were vomiting and burning sensations of the eyes, throat, and nose. The number of people who died in the Bhopal disaster is still unknown. However, a UNICEF report indicates that the number of deaths may be as high as 10,000. UNICEF indicates that of the 200,000 estimated to be affected by the disaster, 75% were slum dwellers and 40% were children under the age of 1. Most deaths were caused by respiratory failure due to either massive internal secretion that clogged their lungs or suffocation. The industrial accident that occurred at Bhopal is an ongoing disaster. Today, at least 120,000 people are still chronically sick from the effects of the chemical release that day. Furthermore, the plant has been left abandoned and full of toxic chemicals, which are contaminating the groundwater, causing illnesses in approximately 40,000 others. A new generation living in Bhopal is being affected by the disaster, from ailments such as fevers, nausea, and exhaustion, to more serious conditions like cancers and birth defects. No evacuation plan was prepared, and a siren used to alert the public around the factory of a chemical release only sounded for a few minutes. Most residents around the factory didn't even wake up to the siren, but instead to irritation caused by the gas. Now, Union Carbide, who owned the factory from which the toxic chemicals were released, and the company's owner, Dow Chemical, refused to clean up the factory and continue to deny responsibility for the poisoning. Greenpeace and survivors of the accident are calling on Dow Chemical to clean up the factory site, to secure long-term medical treatment and rehabilitation for the survivors of the accident, to ensure compensation for the affected people and their families, and to provide clean drinking water to communities in areas affected by contaminated groundwater. Now that you have an understanding of what happened during this disaster in Bhopal, Torrin will explain how the chemical plant operated, Darren will describe what actions and events led to this horrific disaster, and Shalini will explain the technical improvements and lessons that were learned by the chemical industry as a result of the Bhopal disaster.
The disaster at the Bhopal plant occurred because operation of the plant differed to the procedures and maintenance requirements the plant was designed for. I will briefly explain the main processes undertaken at the Bhopal plant, focusing on the methyl isocyanate storage facility, the origin of the disaster. The Union Carbide India Limited owned Bhopal plant produced the pesticide carbaryl under the trade name 7 in Bhopal, India from 1979 until a disaster occurred in December 1984. The plant was located approximately 2 kilometers to the north of the center of Bhopal, set amidst densely populated slums which lacked adequate emergency and technological support. Logistically, the plant's location was chosen because of its close proximity to a reliable source of water at local Bhojtal to take advantage of the railway that would span the country, and because of its central location in India. Under normal operating conditions, the UCIL factory produced carbaryl by reacting monomethylamine with phosgene to produce methyl isocyanate. MIC was then reacted with alpha-naphthol to produce carbaryl. In one section of the plant, carbon and oxygen were reacted to form carbon monoxide, which was then reacted with chlorine to form phosgene. Methylamine and phosgene were then reacted in a separate part of the plant, producing unrefined MIC and hydrochloric acid as a byproduct. Once refined, the MIC entered the storage system in which the disaster occurred. The intermediate MIC was stored in 2 double-walled, partly buried stainless steel tanks, storage tanks 610 and 611. An additional storage tank, 619, was also available to receive contaminated material in case of an emergency, such as a thermal runaway reaction. These tanks were designed for an operating pressure of 4 bar and had a capacity of 55 cubic meters each. The MIC stored in the tanks was transferred via a centrifugal pump around a loop through a fluorocarbon-based refrigeration system to keep the stored MIC near 0 degrees until it was required in the alpha-naphthol reacting vessel. MIC was introduced into this loop from the MIC refining still or from the 2 other storage tanks. Should an overpressurization in the tank occur, a combination of a rupture disc and safety valve on the top of the tank ran to the relief valve vent header, where the gas could be discharged into the atmosphere via the vent gas scrubber and or flare tower, described by Darren in the next section. Stored refined MIC was transferred to the derivatives plant when required by means of a different centrifugal pump, where it was batch reacted with alpha naphthol to form 7-carbaryl, ready to be packaged and dispatched. Under normal circumstances, water was not placed in the same closed system as the stored MIC, as they react exothermically. However, due to a variety of reasons that Darren will go into next, water was introduced on the night of the disaster and culminated in a runaway exothermic reaction that could not be safely neutralized or contained.
Now that we've seen the consequences of what happened and how the plant operated on a daily basis, let's discuss what went wrong. Well, the list of what went wrong at Bhopal is quite long, but the basic scientific explanation is that somehow water entered a tank containing methyl isocyanate, MIC. The water and the methyl isocyanate reacted exothermically, causing an increase in temperature and pressure. This increase was so great that the methyl isocyanate expanded into a gas form, blew past all the safety systems and was vented into the atmosphere. There's been 3 major investigations into the incident at Bhopal. The Indian government conducted its own investigation through its Central Bureau of Investigations. This report has never been released to the public. Union Carbide conducted its own investigations, and an independent investigation was conducted by an engineering consulting firm, Arthur D. Little. All 3 reports agree that the cause of the incident was water entering MIC storage tank 610. However, the reports disagree on how much water entered the tank and how the water entered the tank. The Union Carbide report and the Arthur D. Little investigation suggest that the only way enough water could have entered the tank would have been for it to be deliberately poured in by a disgruntled employee. The Indian government report has never been publicly released. However, the Indian government has supported the theory that the water entered the tank when a section of pipeline was being washed. The initial investigations were hindered by the fact that large amounts of toxic chemicals remained in tanks and had to be neutralised before the investigations could take place. However the water came to be in the tanks, the fact remains that the plant was poorly designed and located in the first instance. The plant design was compromised from the beginning, with the local government authorities insisting that the latest technology electronic warning systems be replaced by analogue gauges so that more employees would be required at the plant, thus providing more employment opportunities for local people. The location of the plant, so near a large population centre, was also raised in Parliament. However, influential politicians with monetary stakes in the pesticide plant dismissed these concerns. The pesticide plant had been running at a loss for some time before the disaster, and many areas of the plant have been forced to cut costs. This cost cutting resulted in a reduction in staff training, a reduction in maintenance on the plant, a reduction in the amount of vital spare parts kept on site, and a reduction in personnel. Many of the plant's experienced personnel had also left the plant for better paying jobs elsewhere. As a result, on the night of the disaster, several safety systems were not in operation. A refrigeration unit designed to keep the MIC at low temperature so that the likelihood of a runaway exothermic reaction would be reduced had been shut off. A gas scrubber that was designed to neutralise any MIC gas that escaped the tanks was shut down for maintenance, and a flare tower that could burn off escaping MIC was offline awaiting a replacement part. A water curtain supposed to spray to the top of the flare tower was poorly designed so that the water could not reach the top of the tower. And even though the factory was located so near a large population, there were no operational warning systems and emergency management plans in place. This resulted in a chaotic response and increased the magnitude of the disaster. The tragedy at Bhopal was not caused by a single failure of one component, but by a chain of events. There was a systematic failure in equipment, personnel and procedures. The failure started at the design process and continued through the operational phase until at the end most of the personnel were as demoralised and broken as the equipment itself. Our team will now discuss what technical improvements would have prevented the disaster and what lessons can be learnt from this tragic incident.
Now that we know what happened in the plant, how it operated normally, and the cause of the accident, let's look at some of the technical improvements and lessons learned so that a similar incident will not occur again. Now, as Darren mentioned, the main cause of the accident was water entering the storage tanks where MIC was stored. Now, this caused the runaway reaction, which released 40 tons of toxic gas into the atmosphere. Now, as mentioned earlier, the presence of water in the MIC storage tanks was due to water entering the sections of pipelines when being washed. Now, this clearly says that minimum care was taken to clean the tanks and no maintenance or little was done on the plant. Now, from this, it's clearly evident that the plant was operated under poor management, and management failed to conduct their regular checks to ensure if safety measures were in place, which resulted in a shut-off of the refrigerator, an inoperable vent gas scrubber, an offline flare tower, and an underpowered emergency water cannon. Now, a technical improvement to ensure that a similar incident will not occur again is to ensure that proper management is in place. Now, competent plant managers also are a technical improvement. Union Carbide failed to keep or appoint experienced workers and lacked in trained staff, which contributed to the disaster. Had there been trained staff in the plant would have been operated safely, and any concerns regarding safety and maintenance would have been addressed. Now, another technical improvement is if strict local laws and regulations were in place. A major cause that contributed to the magnitude of the disaster was the location of the plant. Now, if management had operational warning systems and emergency management plans, the disaster would not have affected the residents in the thickly populated residential area where the plant was located. Now, if local laws and regulations were strict, the plant would not have been in the residential area without appropriate safety measures. Now, let's look at lessons learned. The most important lesson that can be learned from such an incident is finding ways to work together in a spirit of cooperation to reduce or prevent accidents and to enhance the protection of personnel and public. Now, one such development in this process is a widespread adaptation of the concept called process safety. Now, following Bhopal, Congress in India has passed the Clear Air Act amendments. Now, another change that was implemented by the government was the process hazard analysis, which is defined as an organized and systematic effort to identify the significance of potential hazards associated with the processing or handling of highly hazardous chemicals. Now, officials say that since the Bhopal disaster, industries have evolved and embraced the concept of process safety and don't see it as a regulation, but as a good business practice. Now, to conclude our presentation, a simple check for safety by the Union Carbide management was eliminated because they made fundamental decisions to save money at the expense of safety. Now, despite all the efforts put into making safety the #1 priority, no one can assure that the chemical plant and the chemicals they produce today are safer 20 years ago when Bhopal woke up to the horrifying call. But if safety measures were in place in Bhopal's Union Carbide chemical plant on December 3, 1984, it would have prevented the release of 40 tons of toxic chemicals into the atmosphere, thus saving approximately 20,000 lives and much more that are still suffering from its effects today. Thank you.